Okay, 50 to 100. And no, that's not a percentage, and it isn't some far-off timeline. That is the staggering number of new gigawatts of energy needed in North America alone over just the next 3 years, strictly to keep up with the exploding demand for artificial intelligence. To put that into perspective, a single nuclear power station produces about 1 gigawatt. That means we essentially need 50 to 100 brand new nuclear projects just to power upcoming AI data centers. It's wild. We have, very abruptly, hit Earth's AI energy wall.
Hello and welcome to This Explainer. Today we're diving into a concept that honestly sounds straight out of a sci-fi movie, but it is rapidly becoming a multi-billion-dollar engineering reality. We're talking about orbital compute, because, the solution to our earthly energy crisis might actually just be floating right above our heads. But as you'll see, moving the cloud to the actual stars comes with some immense, unforgiving engineering hurdles.
Okay, let's dive into this. Here is our roadmap for today. First, Earth's AI energy crisis. 2. Serving space, not Earth. 3. Power and vacuum cooling. 4. Surviving the orbital environment. And finally, number 5, the geopolitical computing race.
All right, starting us off with Section 1, Earth's AI energy crisis.
Globally, electricity use for data centers is expected to double by 2030, and by 2050, they could consume a full tenth of all electricity used on Earth. That's a massive slice of the pie. Down here on the ground, these facilities are absolute power and land hogs. They require vast amounts of water for cooling, and local communities are increasingly pushing back against the noise and the resource drain. So this is exactly why the endless real estate and practically unlimited solar energy of space are looking so incredibly seductive to the tech industry right now.
Moving on to Section 2, Serving Space, not Earth.
Now, if you're sitting there imagining that launching servers into orbit is going to make your ChatGPT load faster, well, we kind of need to recalibrate our expectations. The harsh reality of physics dictates who gets to use this technology first. As the sources point out, Earthbound cloud services, things like real-time financial trading or interactive AI, rely on absolute instantaneous responses. Because of the sheer distance involved and the absolute limits of the speed of light, the time delays, the latency, make orbital computing entirely useless for those real-time tasks. So instead, the very first true customers for space data centers are going to be space-based. We're talking about processing military intelligence, scientific computing, and supporting other space missions directly out there in orbit.
So the crucial point is something called edge computing. Right now, satellites collect massive amounts of raw data, think high-resolution imagery, and they have to beam all of that raw data back down to Earth just to be processed. By putting AI chips right up there in orbit, satellites can process, filter, and analyze that imagery right there on the edge of the network. They send back only the crucial insights, which saves a massive amount of bandwidth. It's a total game changer.
That brings us to Section 3, Power and vacuum cooling.
Now sure, the sun is always shining in space, but powering an AI data center requires unimaginably massive solar panels. We're talking up to 4 square kilometers in size. And frankly, we don't have experience deploying anything quite that large. But researchers in Singapore are testing an incredible solution: perovskite solar cells. Basically, it's a chemical ink coated onto a surface that makes it cheap, lightweight, and super flexible. It can literally be rolled up tightly, packed into a rocket, and then safely unfurled in orbit to catch all that sunlight.
But hey, generating power? That is only half the battle. The other half is cooling the things down. On Earth, we use air, heavy chillers, and massive liquid cooling water systems to carry away the intense heat that AI chips generate. But space is a near vacuum. There is absolutely no air and no water to blow across hot equipment. Even though the background of space is a freezing minus 455 degrees Fahrenheit, that heat just gets trapped inside the satellite. So engineers have to rely purely on passive radiators, where the heat very, very slowly escapes as infrared radiation.
And this brilliantly illustrates just how tough that is. To put that slow process into perspective, removing just 10 megawatts of waste heat from an orbital data center would require thermal radiator surfaces roughly the size of 2 entire football fields. Just let that sink in. That is a massive, massive amount of surface area that has to be launched, assembled, and protected in orbit.
Which leads us to Section 4, Surviving the Orbital Environment. Because cooling is just one piece of the puzzle. The full checklist of dangers in space is brutal. First, you've got constant radiation that can easily scramble or completely destroy sensitive AI chips, meaning you need heavy shielding.
Second, depending on the exact orbit, these data centers will experience extreme temperature swings several times a day as they whip from blistering sunlight straight into Earth's freezing shadow. Third, orbit is crowded. There are very real, very scary dangers of collision from high-speed orbital debris and micrometeorites that could just puncture and destroy the equipment in a second.
But honestly, the most terrifying bottleneck might just be operational. Think about it. On Earth, data center hardware gets upgraded every 3 to 5 years. It's easy. You just send a technician down the aisle to swap out a server. In zero gravity, hardware refresh cycles are incredibly difficult and wildly expensive. If you can't easily swap out aging chips, your multi-billion-dollar orbital data center might become totally obsolete while its solar panels and radiators are still perfectly fine.
So you might be wondering, with hurdles that high, why on earth are companies trying this now? Well, it's because the economics of launch are changing rapidly. Historically, launch costs were a massive, impassable barrier. But with fully reusable rockets coming online, like SpaceX's Starship, the cost of dropping heavy equipment into orbit is designed to plummet. We're talking going from a break-even of $500 a kilo down to just $10 to $20 a kilo. Suddenly, the math for building orbital infrastructure actually starts to make sense.
All right, finally, Section 5, the geopolitical computing race.
Because building data centers in space isn't just an engineering challenge anymore. It's rapidly becoming a major matter of national security. The source material outlines two very distinct strategies currently playing out. In the United States, the approach is privately led by commercial space startups and giants like SpaceX, StarCloud, and Blue Origin, and they are focusing heavily on commercial AI infrastructure. China, on the other hand, is taking a state-mandated and funded approach. Notably, they have their three-body computing constellation, which plans to launch 2,800 satellites. As noted in the sources, their primary focus really emphasizes national security and technological self-reliance. And experts point out that orbital compute provides immense military and intelligence security advantages simply because these assets sit far, far beyond the reach of traditional physical attacks down here on Earth.
Let's move to and see how this builds toward an ultimate vision for the future. For any of this to actually work, these isolated data centers need to be able to talk to each other. So instead of undersea cables, the connective tissue of this new orbital internet will be lasers. Companies are actively working on beaming immense amounts of data, literally 1,000 times more bandwidth than radio waves, directly through the vacuum of space. Because there's no air, no rain, and no clouds to block the signal up there, lasers are the absolute perfect, unobstructed way to link this massive new space architecture together.
So, what does this all mean? Well, it leaves us with this massive, looming question. We are watching the dawn of a completely new market right now. It is harsh, it is incredibly expensive, and the engineering challenges of vacuum cooling and zero-gravity maintenance are just monumental. But as AI's energy footprint on Earth continues to expand past its absolute limits, the race to space feels kind of inevitable. Will whoever successfully builds this orbital infrastructure first end up controlling the very fabric of the next internet? It's a fascinating thought to leave you with. Thank you so much for joining me for this explainer, and remember, keep looking up.